Basically, temperature is the degree of hotness or coldness of a substance measured on a scale. As you know, temperature scales usually indicate units of degrees Fahrenheit or degrees centigrade or Celsius. At the molecular level, temperature is a measure of the average molecular kinetic energy of a substance. That is, temperature is an indication of the average molecular motion in a substance. Heat is a form of energy known as thermal energy. Thermal energy can be either stored in a substance or transferred from one substance to another. There's an important law of energy called the law of energy conservation. This law states that energy can be neither created nor destroyed, only altered in form. Basically, this law means that all energy has to be accounted for. A temperature change can be measured or felt. Heat transfer that causes a temperature change is called sensible heat transfer. Heat transfer that does not cause a temperature change is called latent heat transfer. During latent heat transfer, there are changes in molecular energy, but these changes don't result in a temperature change. Instead, they result in a phase change. The three phases or states of matter are solids, liquids, and gases. So, sensible heat results in a temperature change, while latent heat results in a phase change. We'll heat a beaker of ice to demonstrate phase changes and latent heat transfer. We'll also use a graph to show the relationship between temperature and heat. The ice is melting, but at first the temperature stays at 32 degrees Fahrenheit. Latent heat is being absorbed by the ice. The latent heat causes the molecules of ice to overcome the molecular forces holding them together. As a result, the molecules move freely as a liquid. But as yet, there is no temperature change. There's only a phase change from solid to liquid. Now that the ice is melted, the addition of heat does produce a temperature change. At 212 degrees, the water boils into steam, but the temperature stays the same. The water undergoes a phase change, but not a temperature change. At 212 degrees, the latent heat causes the molecules to move fast enough to overcome the molecular forces holding them together. When the molecules absorb enough latent heat, they leave the water as steam. Section B represents sensible heat because from this point to this point, the temperature of the water changes as a result of heat transfer. Section A and Section C represent latent heat transfer because there are no temperature changes in these sections, only phase changes. This horizontal line at 32 degrees represents the latent heat of fusion or melting. The latent heat of fusion is the amount of heat required to melt a substance without a change in temperature or pressure. This point represents ice at 32 degrees, and this point represents water at 32 degrees. The line between these points represents an ice-water mixture. This horizontal line represents the latent heat of vaporization. The latent heat of vaporization is the amount of heat required to vaporize a substance without a change in temperature or pressure. This point represents water at 212 degrees, and this point represents steam at 212 degrees. So the line between these points represents a water-steam mixture. In the example we just saw, heat was added. If heat is removed, the heat transfer line moves in the opposite direction. That is, when heat is removed from steam, the steam starts to condense into water. Under these conditions, heat is removed from steam, and the steam condenses rather than vaporizes. So this line represents the latent heat of condensation. The latent heat of condensation is the amount of heat that has to be removed from a substance to condense it without producing a change in temperature or pressure. Then, when heat is removed from water, there's a sensible heat transfer, and the water temperature drops until it reaches 32 degrees. At that point, any heat removed is latent heat, so the temperature remains at 32 degrees. This line then represents the latent heat of freezing. The latent heat of freezing is the amount of heat that has to be removed from a substance to freeze it without producing a change in temperature or pressure. When a liquid boils, a phase change occurs. A substance changes from a liquid state of matter to a vapor state. The boiling point of a liquid is affected by temperature and pressure. To show how temperature and pressure affect boiling points, we'll use water as an example, but the same basic principles apply for all liquids. The boiling temperature of water is different at different pressures. For example, at atmospheric pressure, water boils at 212 degrees Fahrenheit. But at pressures lower than atmospheric, the boiling temperature decreases. At pressures above atmospheric, the boiling temperature of water increases. To show how temperature, pressure, and heat are related to the boiling point of water, we can construct a graph. The vertical axis represents temperature in degrees Fahrenheit, and the horizontal axis represents heat. We'll use a pound of water as a standard, so the heat's measured in BTUs per pound. A BTU is the amount of heat needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. Atmospheric pressure is 14.7 PSIA. At atmospheric pressure, water starts boiling at 212 degrees Fahrenheit. On our graph, this is the point at which water first starts boiling at atmospheric pressure. And this is the point at which all the water is boiled into steam. This line represents the amount of heat required to boil all the water. So this line represents the latent heat of vaporization. For 1 pound of water at atmospheric pressure, it takes about 970 BTUs of heat to boil all the water into steam. Now let's take an example in which the pressure is less than atmospheric. At this point, the pressure is 4.9 PSIA. At this pressure, a pound of water boils at 162 degrees. In addition, the latent heat of vaporization is around 1001 BTUs per pound. So when the pressure is reduced, water boils at a lower temperature. However, it takes more heat to boil all the water into steam than it takes at atmospheric pressure. At lower temperatures, the water molecules move more slowly. As a result, it's harder for them to boil and escape the body of water as steam, so it takes more heat to change the water completely to steam. Now let's look at a pressure that's higher than atmospheric, 114.7 PSIA. At this pressure, water won't boil until it reaches 338 degrees. Under these conditions, the latent heat of vaporization is about 881 BTUs per pound, which is less than the latent heat of vaporization at atmospheric pressure. At higher temperatures, the water molecules move more quickly than they do at lower temperatures, so it's easier for the molecules to boil and escape the water as steam. In other words, it takes less heat to change the water completely to steam. As the pressure and boiling temperature of water increase, the latent heat of vaporization decreases. There is a point, however, at which the latent heat of vaporization is 0 BTUs per pound. This point occurs at a pressure of 3,206 PSIA and a boiling temperature of 705 degrees Fahrenheit. This point's called the critical point. Above the critical point, water flashes to steam, but there is no latent heat transfer. Above this point, water exists as a superheated vapor. A superheated vapor is a vapor whose temperature is higher than its boiling temperature. We can draw a curved line that connects these points. This line is called the saturation curve. The points to the left of the critical point represent liquid at the boiling temperature for a given pressure. The points to the right of the critical point represent vapor at the boiling temperature. In this topic, we examined the concept of phase changes. We contrasted latent heat with sensible heat, and we looked at the effects of temperature and pressure on the boiling point of water. Let's stop for a moment so you can answer a few practice questions. A temperature change can be measured or felt. Heat transfer that causes a temperature change is called sensible heat transfer. Heat transfer that does not cause a temperature change is called latent heat transfer. At higher temperatures, the water molecules move more quickly than they do at lower temperatures, so it's easier for the molecules to boil and escape the water as steam. In other words, it takes less heat to change the water completely to steam. As the pressure and boiling temperature of water increase, the latent heat of vaporization decreases.